The vulnerability we're going to talk about is almost impossible to find, even if I tell you exactly which lines to look at. But take a look for yourself.
So, this bug was discovered in FreeBSD, which is an open source operating system. And this is a simplified version of the code, but functionally the same. So if you want, pause the video now and try to find it on your own. So did you find it? Well, if not, I tell you the line. It happens in line 7 and 8. Now, give it a second try. Okay, if you found it on your own, it's beyond me how your brain works. But for us mortals, let's try to understand what's going on here. So what problem is this piece of code trying to solve? Well, as I already said, this bug was found in the kernel of FreeBSD. And when a kernel is running, it is stored somewhere in memory. And this includes the kernel code, but also sensitive data like passwords or secret keys. Of course, there are other programs running on the same machine too. And they should be allowed to read from memory, but not without restrictions. For example, other programs obviously shouldn't be allowed to read the password region, because if it were allowed, it could just read all the passwords and send them anywhere. But sometimes it's necessary that a program is allowed to read a very specific region in the kernel space. And in this case, we need strong safeguards that ensure that only the intended region can be read. And this is exactly what this code does. But how does it work? Well, let's go through the code. So first, we have a memcopy function. And this is a standard function that copies a memory block of size n bytes from the source address to the destination address. So for example, if we provide this address as the source address, this as a destination address, and a size of 1 kilobyte, which is this in hex, then the memcopy function copies this 1 kilobyte region to the destination address. Okay, back to the code. This part defines a character array of size 1 kilobyte. It's the kernel region that the user is allowed to read. Let's say it's located at this address in memory, and let's assume that right after that is some memory with passwords. Now, the copy from kernel function does the safeguard check and the actual copying. The user has to provide an address of a location where the data should go and how many bytes should be copied at most in case not the entire region needs to be copied. Now, a malicious user could try to misuse the length argument. To do that, the user could try to provide a large value for the length in the expectation that the copy from kernel function blindly copies the desired number of bytes. For example, the user could provide a length of 2 kilobytes and hope that this entire region is copied. But the safeguard check in line 7 blocks that. And it works like this. When the user provides a size, this part checks whether the provided size is larger than the size of kbuf. If it is, it stores the maximum size that is allowed to be copied in safe lang, which is 1 kilobyte, so the size of the entire kbuf region. If, on the other hand, the provided value is smaller than the size of kbuf, it stores the provided value in safe lang. And then savelang is passed to the memcopy function. And by this, it should be ensured that we never pass a size that is larger than 1 kilobyte.
So we're safe, right? Well, no. There's a sneaky exploit that breaks this logic. But how? How is that possible? Well, to understand that, we have to understand how computers store numbers.
So savelang is an integer, and we have two types of integers: unsigned integers and signed integers. So unsigned integers are non-negative whole numbers, and signed integers also cover negative values. And these are some integer type specifiers that we can use and see. Now, unsigned integers are stored in the unsigned binary format. So if we have a byte like this and we want it to represent an unsigned integer, we can convert it as follows. First, we need to know that each bit represents a power of 2. The single bits then determine whether the corresponding power of 2 contributes to the value or not. So in this example, since this bit is 1, we add 2 to the power of 7, which is 128. The next bit is 0 and contributes nothing. Then, with this bit, we add 2 to the power of 5, and so on. And if we add all these values up, we get 185. So this binary number represents 185 in the unsigned binary format. Alright, that means when we have 8 bits like we have here, we can store numbers from 0 to 255. And if we use more than 8 bits, we can store larger values. For example, with 16 bits, we can store the numbers from 0 to 65,535, and so on. But we cannot store negative numbers in this way. So if we want to store signed integers, we need another format. And the format used for this is the so-called 2's complement format. So let's take a look at the binary value from before again. And like before, each bit represents a power of 2, but with one small difference. The most significant bit in the 2's complement format is negative. So if we evaluate what this bit contributes, this time it's minus 128, and the rest just stays the same. Now, if we add all the values up, we get minus 71. And in this format, if we have 8 bits like this, we can store the numbers from minus 128 to 127. And again, if we use more than 8 bits, we can store a wider range of values. For example, with 16 bits, we can store values from minus 32,768 to 32,767. And also important to notice that in this format, the smallest value always looks like this in binary. All the ones always represent minus 1. All zeros is still 0, and the largest value always looks like this. But how does that help us to circumvent the length check? Well, let's take a closer look at the memcopy function. So memcopy expects the length in size t, and the type size t is an unsigned integer. But our length variable here is of type int, which in C is a signed integer. And that's really bad. But why? So because saveLang is of type int, it's stored in the 2's complement format. But if the memcopy function expects an unsigned integer, any binary value given to the memcopy function is interpreted in the normal binary format. So the binary value that we hand over doesn't change, but how it's interpreted changes. And that's obviously not good, but it's also not automatically a security problem. For example, if we try to read more data than we are allowed by entering a length of, say, 2 kilobytes, saveLang is still only 1 kilobyte. And if we transform that to a 16-bit binary number, it looks like this. If we then interpret this binary number using the normal binary format, we still get 1024 as a result, so nothing breaks, even though the conversion was not correct. But who says that we can only choose positive values for the length? After all, lang and saveLang are signed integers. So if we choose minus 2048, the check says, well, minus 2048 is not larger than 1024, so let's store minus 2048 as saveLang. So then, minus 2048 is stored in the 2's complement format, which looks like this, and then it's handed over to the memcopy function. But this function, as we've seen, expects an unsigned integer, and it interprets any binary value that it receives as such. So when it receives this binary value, It thinks that it received this huge number. And then it tries to copy way more than we want it to.
So, can an evil hacker now extract any data using this bug? Not quite. Turning this bug into a working exploit is hard. For example, the best we can do on a 64-bit machine is to pass this many bytes to the memcopy function. That is about 18 exabytes. That's a lot. And to be able to copy that much, we need that much memory. And you've seen today's RAM prices, right? On the 32-bit system, it's a bit more realistic because we need 4 gigabytes, but still, these devices are not really common. But even if you find one, there are other conditions that have to align. So in practice, exploiting this bug is quite unlikely. But who knows? Who knows?